My name is Lutz Wiegart and I'm a scientist at the National Synchrotron Light Source II. And the title of my talk is Staying in Shape and Staying Connected. But no worries, I'm not going to talk about going to the gym or using social media. I'm going to talk about 3D printing, and you will see in a little while how that connects to the title. So many of you might be familiar with this type of 3D printing that is shown here. Maybe many of you even have a 3D printer at home. But 3D printing is really much more versatile than this. So today you can really quite literally 3D print a house or a steel bridge over a canal, something that's known today as digital architecture. 3D printing is also impacting the arts. It can either create new art or it can recreate art that has been lost. 3D printing can also create really large parts, not just the tiny parts that you might print at home. So there's been entire cars have been printed at Oak Ridge National Lab that can actually drive. And if you can print cars, we can obviously also print boats. On the other end of the spectrum, we can also print really tiny parts, like these artificial heart valves that are being printed for biomedical applications. So what is it that makes 3D printing so revolutionary? For one, it's the economical use of materials and the design flexibility that it gives you. It also allows you unique material combination and to make shapes that you can't really make with any other manufacturing method. And the key to all of this is the fact that 3D printing is an additive method. So you're adding one piece of material at a time as you make up a part. And you can see that quite well. If you zoom into a big part like this car part, you will see that it's made up of stacked filaments that are on the micro to millimeter to centimeter size. And if you zoom into that even further, you could see that on the nanometer and micrometer scale, these parts are made up of molecules, nanoparticles, and there are interfaces in between them, and so on. And this last zoom in you can't do with your magnifying glass, but you can do that if you have a synchrotron like the National Synchrotron Light Source II. And if you put a 3D printer on this machine, on one of the beamlines there, then you can even watch 3D printing processes as they are happening. And that's what we did to tackle one of the most prominent problems in 3D printing. And I said additive is a key to many of the big advantages of 3D printing, but it's also one of its bottlenecks. And that's quite well illustrated by this part here, which quite frankly resembles a piece of puff pastry. And what's happening here is that the individual filaments and layers that have been printed are actually coming apart. And that's happening because as they are being printed, they solidify and they have very bad adhesion with each other. So as the part is being printed, it's more like stacking solids on top of each other. And we all know stacking solids can be quite a fun, but it's not a very stable thing. What we rather want is the individual layers and filaments to have like a molecular version of interaction like a Velcro tape, that they entangle and create connection. So that brings me to the first question: how do we make the filaments in a 3D print stay more connected? Well, I said one of the problems is that the filaments solidify already on their own while they're being printed. So an obvious solution is let's go to a material that we can solidify on demand once we have printed the entire part. And that can be done with something like a molecular building kit, which you can think of as the equivalent of a stick building kit for kids. And while that stick building kit is assembled by hand, the molecular equivalent can assemble over time by itself, or you can drive it with external stimulus, like for instance heat or light of a certain wavelength. And when you do that, you end up with a 3D network of the assembled molecules. So if you apply that to 3D printing, you could print your part, in this case 2 filaments, then you wait a little bit, let the molecules diffuse across the filament interface, and then in this case you use UV to create a 3D network, and you have a strong connection across the interface. Voila. There's a little problem with that though. In order for the molecules to diffuse across the interface, the material needs to be a little bit liquid. And you can imagine if you print a liquid, you get a puddle, not a part. You can play some tricks and make the material behave more like toothpaste, and then you can certainly print a single filament. But if you ever try to print a car out of toothpaste, you'll probably figure out that will collapse under its own weight. So that brings me to the second question: how do we make the part stay in shape until we induce the final solidification of it? Imagine now you have 2 molecular building kits that you can actually mix and that react to different stimulus. Then you can print a filament of that, and you can shine UV on it, and you can build a network in one of those molecular building sets, and you can do that with the next filament. And after that, you have like a skeleton in each individual filament that keeps the part in shape. You don't have anything going across the filament interface yet, but you still have the second set of molecules that can diffuse across those interfaces because they are not yet assembled. And after the whole part is done, we just assemble that into a three-dimensional network. All right, that looks pretty good in my little animation here, but how can we actually show that this is something that we can do in actual materials? I mentioned earlier, if we can put a 3D printing platform on a synchrotron beamline, we can watch these processes in situ. And that's what we did. We investigated the 3D printing process, mapping out the filament with a tiny X-ray beam, 1/10 of the size of a human hair. And what we obtain is a map of the filament. We have the height, we have the time, and we have the mobility of the material that we track as a parameter. Okay, so if we start out with our toothpaste-like material and we don't do anything to it, we see that we overall have a very high mobility of the material, but we already in a single filament see settling and collapse. If you switch on the UV to introduce the skeleton formation, we see that on the top part of the filament, we actually get a skeleton, but on the bottom part, because of the UV gets absorbed throughout the filament, the UV dose is not sufficient to build that skeleton, and we still see signs of collapse there. So once we crank up the UV dose to an adequate amount, we can actually form the skeleton throughout the entire filament. That happens after about 200 seconds of time. After that, the skeleton is fully developed, but we still have mobility in the filament due to the second species of molecules that haven't been assembled yet into a 3D network. How to build a part then? If we print another filament on top of the first one, we can clearly see at the very beginning that there is a distinct interface between those two filaments, and that's due to the fact that the skeleton hasn't been built in the first one yet. After 200 seconds, however, the skeleton has also been built in the top filament, and afterwards there is no difference in the mobility anymore across those filament interfaces. And that's exactly what we wanted, going back to the schematic that I showed earlier. We are now exactly in the state where each individual filament is supported by a skeleton, but we still have the second set of molecules that is not assembled yet, which we can do that by doing a heat treatment, and after that we end up with a solid part. And in a solid part we can't measure the mobility anymore, but we can do X-ray microscopy and look for defects in those parts. And if one does that, we see the defects like voids are shown in these little colored blobs here, and it's actually easier to see if I remove the material. So on the left side we can see our double molecular system, and there the voids and defects are really like tiny, and they are spot-like, and they are not really affecting the mechanical properties of the part much. Very contrary to conventional printing, where we see defects and voids running all along the filament surfaces, and that really makes for a weak mechanical part. Okay, that was an example of a relatively simple system that we investigated. Let me finish with an outlook into the future. And what people are starting to do is they're printing voxelated materials. These are materials where they can, during the printing process, change the composition of the material that they are printing on the length scale of 100 micrometer. Again, that's a human hair. So we can end up with materials that change the properties on length scales of 100 micron. And that's very interesting, for instance, for 3D printed electronics, but also for applications like soft robotics. And what we do is we are combining our experimental capabilities and our analysis with machine learning methods in order to investigate the processing parameter and material composition phase space that comes with this type of printing to help developing the next generation of 3D printing.